Thomas Jefferson National Accelerator Facility is a laboratory for basic nuclear physics research operated by the U.S. Department of Energy. At Jefferson Lab, scientists can advance our understanding of matter itself by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
Good evening. Welcome to Jefferson Lab. I would like to introduce tonight's Science Series guest speaker, Tom Siegfried, science editor for the Dallas Morning News. He began his career in science journalism more than 20 years ago after graduating summa cum laude from Texas Christian University with majors in journalism, chemistry, and history, and earning his master's degree from the University of Texas with a major in journalism and a minor in physics. He is currently editor of the highly regarded weekly science section of the Dallas Morning News, and he oversees internships that are widely regarded as the place to be for aspiring young science writers. He has won numerous writing awards and sits on the boards of national science writing organizations. His first book, The Bit and the Pendulum, was published in 2000. Tonight, Tom Siegfried shares with us insights from his new book, Strange Matters. Science is full of examples of pre-discovery, the prediction of new phenomena in advance of any physical clues to their existence. Antimatter, black holes, and the expansion of the universe were all discovered by physicists studying squiggles on paper. Now, predictions of strange quark matter, invisible stars, and new dimensions of space and time set the stage for the biggest science headlines of the 21st century. Ladies and gentlemen, please welcome Tom Siegfried.
Well, thank you all for coming. This is a bigger crowd than I'm used to speaking to, so I decided I probably should have two jokes instead of just one to start out. The joke I usually tell is most appreciated by scientists when I speak to them about being a science journalist, and they are always skeptical about whether science journalists can get things right. I said, no, of course we do, and we're always very careful about that. In fact, I had a story to tell that I thought illustrated that pretty well. It was about a physicist, philosopher, and mathematician who were riding in a train through Scotland. And I believe it was the physicist who looked out the window and saw a black sheep and said, look, there's black sheep in Scotland. And the philosopher turned and said, well, there's at least one black sheep in Scotland. And the mathematician said, well, there's at least one black sheep, there's at least one sheep that's black on at least one side in Scotland. Well, while they were talking, there was a fourth person in the train car who at this point had taken out a notebook and was scribbling down, and the other three looked and said, hey, what are you doing there? So, well, I'm a science reporter, and I'm taking notes, working on the lead for my story. And they said, what story? Well, what's it going to say? I said, well, I'll read it to you. It says, a half-white, half-black cloned sheep, probably the result of illicit genetic engineering experiments, was seen roaming free in Scotland, scientists said today. So we strive for accuracy and responsibility in our reporting. I have to tell my other favorite joke because it's a physics joke, and this, Jefferson Lab is a physics lab, and it's about the two most famous physicists of the last century, Niels Bohr and Albert Einstein. Niels Bohr, who explained the atom, and Einstein, who explained gravity in the universe. They always engaged in deep arguments about some of the fundamentals of physics, especially quantum physics, and they were always unable to reach agreement. And so after one of their particularly vigorous arguments, they decided to go for a hike to cool off. And they were hiking in the woods, and they came across a big bear, and immediately Niels Bohr pulled off his backpack and pulled out a pair of super high-tech running shoes and started lacing them up. And Einstein's going, I hate to tell you this, Niels, but there's no way you're going to outrun that bear, even with those shoes. Niels looks up and says, I don't need to outrun the bear, I only need to outrun you. So anyway, so much for the physics jokes. That joke really belonged to Leon Letterman, the famous Nobel laureate physicist, but I thought it was worth borrowing. My book, Strange Matters, is about science about scientific things in the universe that haven't been discovered yet. And when I first told people I was working on that book, I got a lot of response to the effect of, that didn't sound like such a promising thing to fill up a whole book about. And I thought about it a little, and they had a point. To write about things that haven't been discovered yet is a little bit challenging. So part of the book, and the first part of my talk tonight, will be showing you why I think it's worth paying attention to the second half of the talk. Why would you want to pay attention to somebody who was going to tell you the things that hadn't been discovered yet? Well, I think there's a good reason, and I think the story of science that history tells almost forces you to believe that's a worthwhile thing to do. This is actually the cover of the paperback version of the book, which won't be out until the spring, but it looks nicer than the hardback, so I thought I'd use this. And actually, I didn't discover this until after I wrote the book, that as Strange Matters for a title, I had been anticipated by a previous author, and I unfortunately cannot think of any way that anything I write about has anything to do with Macbeth, so I can't make much use of this, but I found it kind of interesting. More appropriate literary allusion, I thought, was one I found from William Blake, who apparently was not very fond of science himself, but in one of his works, he has this very nice line that what is now proved was once only imagined. And in fact, I think the history of physics and astronomy and the study of the universe is full of examples of just this very point, and that's what I'm going to talk about tonight. As you heard, the idea that I'm expressing is that many of the great discoveries in science are really what I would call pre-discoveries. They're things that somebody has figured out before anybody has actually found any evidence for them. Things that are out there in the universe that are strange, very strange, bizarre, almost unimaginable, yet somebody figured out a way to imagine their existence before anybody actually found them. And this is a little bit different from the way I think people think of science as working. I mean, I think the general idea is, and maybe some textbooks perhaps convey this idea, that people do experiments to do science. They go out and do observations, do experiments, find things out that way. And then maybe some theoretical scientist will come along and try to devise an explanation for what you found. And of course, that sort of thing does happen in science. But there's more to it than that. There is this role for the imagination and creative thought in science that produces ideas for things before anybody has done any experiments or found any evidence or any clue that they existed. So I'm going to talk about some of those examples historically first so that you can see that I'm not just making all this stuff up. One of my favorite and earliest examples, I think, of this is the pre-discovery of electromagnetic waves, like radio waves. James Clerk Maxwell, a famous Scottish physicist who, as far as I know, never commented on black sheep, figured out by studying the relationship between electricity and magnetism that light was just a form of wave that had electric and magnetic components to it. And he deduced from that that if light is a wave of this nature, an electromagnetic wave, there might very well be other kinds of electromagnetic waves out in the universe that nobody had ever seen. And this is in 1865. Nobody had any clue about radio waves back then. Nobody had any idea such a thing as radio was possible. And so Maxwell mentioned this, and other scientists realized that he had suggested this possibility. And one who took it most seriously, I think, was Heinrich Hertz, a German physicist, who in 1888 succeeded in producing radio waves in his laboratory, proving that Maxwell's idea that such waves might exist was in fact true. Even though there had been no evidence for them, Maxwell figured out they might exist. Hertz looked for them and found them. And so now, today, we know that there are all kinds of electromagnetic waves. Use this pointer. It says danger. U.S. government property, that's why it's dangerous. So here's light in the spectrum with a certain wavelength, and then we know that beyond what is visible, we know there's such a thing as ultraviolet radiation that we can't see, and infrared radiation, and the radio waves out here that Hertz figured out, and there's more now that we know there are smaller waves, microwaves. And off this way, we now know there are other things like X-rays, which were discovered a few years after Hertz discovered radio waves. But again, the key point here is that Hertz just didn't accidentally discover these radio waves looking for stuff out in nature. He knew that Maxwell said these things might exist, and Hertz found them. Another great example, and this is a little more technically complicated, but still I think very interesting, was Riemann, a German mathematician who devised a different form of geometry. He wasn't the first to devise a different form of geometry, but he was the one who I think gave the most thought to what he was actually doing. In school, even for 2,000 years, even school today, people are taught geometry as it was figured out by the ancient Greeks, in particular as it was compiled by an ancient Greek guy named Euclid. It's very elegant mathematics. The system of geometry works very well for most of the things you have to do. And it was once regarded as working so well and being so perfect that there was no way you could even question it. But in the 19th century, some mathematicians began to wonder, maybe if you change some of the assumptions that Euclid had built his whole system on, maybe you could find a way geometry could be a little different. And in fact, Riemann explicitly pointed out that for all we know, and geometry seems to work in the regular world, but what if you went to very small distances? Or for that matter, extremely large distances. Maybe Euclid's geometry wouldn't work there. And he worked out the math to describe how it might be a different way. For a long time, people thought that was a nice, fun thing to do, but could it possibly be useful or meaningful for anything? Well, one guy who took it seriously a few decades later was Einstein, who actually was not such a hot mathematician himself. He was a really good physicist and really brilliant thinker, but he always needed a little help with his math. A friend of his looked up Riemann's work and came and told him, hey, you should look at this stuff by Riemann, and Einstein did, and that was the clue he needed to make his general theory of relativity work out right and explain gravity. But again, Riemann Riemann was not out doing experiments. He was working with little squiggles on paper and figuring out the math that told him that the world might be a different way than from what everybody thought it was. A few years after Einstein did his work on general relativity and explaining gravity and explaining basically the nature of space and time, a Russian mathematician came along and said, you know, Einstein's equations are very interesting, and in fact, they describe a universe much stranger than the universe anybody thinks we live in. Einstein himself suspected something was fishy in his equations. In fact, he looked at his equations and applied them to the whole universe and said it showed that the universe might be changing in size. And Einstein said, everybody knows the universe is just the universe. It's always the same as it always has been. It doesn't change in size. So he added something to his equation to fix that problem. Well, Friedman came along a few years later and said, you know, Einstein didn't know what he was doing. He didn't need to do that. You could actually describe with the equations universes that were doing things like expanding and getting bigger all the time. So in the early 20s, Friedman wrote his papers suggesting the possibility that the universe could be very different from what we thought. Nobody at this point had done any kind of observations to show that there was something like this going on in the universe. But a few years later, Edwin Hubble, whose name is famous today because he was who they named the Hubble Space Telescope after, figured out by looking at the distant stars and the distant galaxies and how they were moving that in fact the universe actually was getting bigger all the time. It was expanding, just as Friedman had suggested by figuring out the implications of Einstein's equations. It was the squiggles on the paper that told Friedman the universe might be expanding. Only later did anybody actually look out in the universe and see, yep, sure enough, the universe actually is expanding. So there were other examples of this. I'm going to go through them a little more quickly now to get into the meat of the story. But if you've heard of antimatter, if you ever watched Star Trek, the engines work by antimatter. There's matter and there's antimatter, and when the antimatter hits matter, they go poof, give off a lot of energy. But before 1930 or so, nobody had ever dreamed of the existence of anything like antimatter. It was not something that people had ever encountered in any experiment or observation. But Paul Dirac, a British mathematician and physicist, was trying to work out the math for describing electrons. And in his equations, he came to a point where, and if you've had algebra, you all probably will remember this. If you take a square root of a number, there's two roots. There's the positive and negative root. And because the negative times the negative is a positive, if you've seen Stand and Deliver, the guy keeps saying that over and over again. And so most physicists knew that this part of the equation existed, and if you were calculating the energy of an electron, it had a square root and it would be a negative or a positive. And they said, well, the negative doesn't make any sense for something to have less than zero energy. We'll just throw that part away and we'll take the other answer. Dirac said, no, you can't do that. Dirac was a very stubborn guy. He said, if it's in the equation, there must be something to it. So Dirac set about trying to figure out what it would mean. And so Dirac decided that maybe electrons can have negative energy, less than zero energy, but if they did, we couldn't see them because we can only see things with positive energy. So maybe there's a whole ocean of electrons out there with negative energy that we won't know about, just for the same reason a fish doesn't know it's living in an ocean full of water. I mean, it's just like nothing. The fish, water is just what's everywhere. There's no point for the fish thinking about water. We don't think about these negative energy electrons. But Dirac said, suppose something came along and knocked one of those electrons out of the ocean and left a little hole where an electron had been. Now, think if you're a fish. If you're a fish, you think water, nothing of it. But if a bubble comes by in front of you and you're a fish, you would say, what do you know, a new subatomic particle. And if you were one of the smarter fish, that's what you would think. And so Dirac said, if you knocked an electron out of this sea of negative electrons that we don't see, we'd see the whole. And since electrons have negative charge, what we would see is what looks like a bubble or a particle with positive charge, the opposite charge of the electron. And so that would explain antimatter, because then if a regular negative electron came along and saw that gap, it would fall into the hole and go poof and give off energy, and it would look like it was disappearing because it went back down into the sea of negative energy. So Dirac made this, I'm shortening the story because his first couple of tries screwed up. He got the wrong mass and everything. But finally he figured out that you could have an antiparticle for an electron, an anti-electron, or it can be called a positron. Same size as an electron, but the opposite electrical charge. Now, the funny part of the story is that there was a guy working in England with Dirac who was studying cosmic rays and had some really strange pictures of the tracks of cosmic rays with weird curving lines, and he showed them to Dirac and said, "What? I don't understand this." And Dirac said, "Ah, that's the antimatter electron right there." And so the guy said, "Nah, it's stupid." He threw the pictures in the drawer and didn't ever say anything about it. But the next year, an American took his pictures of the cosmic rays, found this weird curving track, and won the Nobel Prize for discovering the positron because he recognized that this was, in fact, the new subatomic particle that Dirac had predicted. Pauli and the neutrinos, I'll just skip over quickly. This is another case where a physicist predicted the existence of a particle nobody had ever dreamed of. And in fact, Pauli himself said it was such a weird particle, it would be so hard to detect that nobody could ever find it. It was stupid of him to even have said so. But a few decades later, Fred Reines did figure out a way to detect the neutrino, and a few decades after that, he won the Nobel Prize. And this is one of the recipes scientists will give you for how to win a Nobel Prize. More recent example is the prediction of the existence of quarks, which are, of course, very famous particles around here at Jefferson Lab, where they study quarks all the time. These were particles that nobody dreamed could exist before 1963 or 4, when Murray Gell-Mann, a very famous physicist, was trying to figure out why there were so many different kinds of particles in nature. There were all bunches of different kinds of particles in the nature by then. Back when Dirac was predicting that anti-electron, there were only two. There were protons and electrons. So it was really bold of him to say that there was another particle. But by the early 60s, there were 100 particles or so. And Murray Gell-Mann was trying to figure out why are there so many. Well, he figured out that if there was yet a smaller kind of particle that you could make some of the bigger ones out of, you could explain a lot of the particles. And in fact, so he coined this name quark to describe these smaller particles. He was just playing around with the particles, as he told me, and said that, it was kind of like, you've seen the periodic table of the elements. He was kind of building a periodic table of the particles, and from that he deduced that there must be these things called quarks that make up a lot of the particles. So in his day, he figured out there were at least 3 for the particles that existed then. Now we know there's 6 different kinds of quarks: the up quark and the down quark, the charm quark and the strange quark, the top quark and the bottom quark. Those guys are really clever at coming up with names. And a few years after Gell-Mann suggested these existed, there was evidence began to come in from the experiments, and then eventually the others were discovered. And now we are all pretty confident that the whole idea of quarks is correct. The quarks are very strange particles, though. They come in a variety of flavors and color. The types I called are called flavors. They come in versions called colors. They have fractional charges, all this stuff. But an interesting thing, they almost always, until a few months ago, somebody would have gotten up here and said they only come in packages of 3 or 2. Some particles made up of 3 quarks, some particles made up of 2 quarks, or technically a quark and an antiquark, but basically packages of 3 or 2. You never can get one off on its own. You can only have packages of 3 or 2. But this year, of course, here at Jefferson Lab, there were experiments, as well as in Japan and elsewhere, that confirmed yet another example of prediscovery by some Russian physicists who in 1997, now all those who are here for extra credit, this is going to be the question they're going to ask you, so you can prove that you were here. You're going to have to know the answer to this mass prediction. These Russian physicists predicted the possibility of a particle that contained 5 quarks, and that just this year was in fact confirmed by physicists here at the Jefferson Lab. There it is. I don't need that pointer. It's dangerous. The pentaquark is up there in the middle of the picture. So now, what I've done so far then is to give you examples of how it would be possible for really, tuned-in science journalists to figure out what the future headlines would be, because they could see these guys making these theoretical predictions and say, hey, that's a good prediction. Maybe somebody will go out and find it for sure, and then it'll be a headline and a big story. So, but what I'm going to tell you the rest of the time tonight is what I think are going to be some of those headlines of the future, or at least some that are possible. I say in my book, I've got a bunch of these that are possible for coming headlines of the future, things that have been predicted that will be discovered. And I guarantee in my book at least one will actually be discovered. I'm just not saying which one it's going to be. And I'd like to claim that it's already come true, but I don't think I will be really willing to do that. In any case, these are some of the things that you might be reading about in the future. And these are some of the strangest things you could imagine. And in fact, nobody would believe any of these things if it weren't for the fact that there are so many examples, like I've shown you, where strange things have come to be true. So, I put my little estimate for the years in which this has happened. I know I said this was going to be headlines from the future, but this would have been the future when I was writing the book. 2002 book wasn't done yet. The book was done, came out. And this headline actually has appeared. Last year, there were reports from some NASA researchers of a strange kind of star out in space that people thought was a neutron star, which is basically a very dense thing left over after a bigger star explodes. Big stars out there will blow up in what's called a supernova, and they leave a dense little cinder behind where the mass of a star like as big as the sun, the mass of the sun is crunched down into a little ball a few miles across. And presumably that is so dense it would have to be like the neutrons that are in the nucleus of an atom. Well, measurements of one of these stars, actually two of these stars I think, gave people reason to believe that it was even denser than that. And instead of being made of neutrons, it was actually, like this neutron star would be, it was actually made of a new form of matter made up of a different kind of combination of quarks. Now, you'll recall that we had those 6 quarks. The first two, the up and down quarks, are the ordinary, common, everyday quarks. They're what makes up protons and neutrons, so they make up most of your body and all the ordinary matter you see. The third kind quark on the list, the strange quark, is one that's only usually found in all kinds of strange particles that aren't ordinarily found in matter. But there are calculations that suggest you could make matter of up, down, and strange quarks mixed together, which would be very dense and just as stable as ordinary matter and could actually exist out in space, maybe in the form of one of these neutron stars that instead of being a neutron star is really a strange quark star. Now the sad thing is, I predicted in my book that this would be discovered and they announced it, but the sad thing is nobody believes them. So it remains to be seen whether evidence will come in that convinces anybody. The arguments that these stars are quark stars, it's just not a very airtight case. It's kind of got too many loopholes in it. So nobody really believes it yet. So I won't claim that as victory yet. However, there's another possibility for finding strange quark matter in space. Suppose these stars existed, and suppose 2 of them collided and went and they kicked off all kinds of splatter of strange quark matter out through space, maybe in the form of tiny little nuggets. If so, these little nuggets, these strange quark nuggets, could fly through space, you know, and some of them might be heading this way. Now, should you worry about that? Probably not. One that would be really tiny, maybe the size of a blood cell or maybe a little bigger, you know, than that, hardly visible, would weigh a ton. If it was a little bigger than a blood cell, it would weigh several tons. And so you've got something that's this small, weighs that much, heading for the Earth. It would go through the Earth something like, you know, shooting a bullet through a bowl of Jell-O. The Jell-O is not going to stop the bullet. In fact, the Jell-O is going to hardly know the bullet went through. It's just going to shudder a little because the bullet will go through so fast, the Jell-O is just going to shake a little bit and like nothing happened. Well, so if one of these nuggets went through the Earth, what would happen? Well, this is a map. Now I need this pointer. I'm going to risk it. This is a map showing earthquake detector stations, seismographic stations, where they detect shaking of the earth as ways of detecting earthquakes. And they're all over the world, these stations. These are some in Australia, some in South America, that on the 24th of November, 1993, almost 10 years ago, try to remember where you were on that date, it could be important. These stations recorded a very strange set of signals. At this time, universal time or whatever, it appeared that some earthquake-type event started sending signals out, waves out, and at this time, and along this line, all during this 19-second period, waves were coming out. Not from one single little point where an earthquake might have been happening, but waves were emanating from what appeared to be a line and a time frame that looked like it took about 19 seconds. So what could that have been? Well, obviously, it was a strange quark nugget coming through space, hitting the Earth off the coast of South America, exiting again off near Antarctica. Just like that bullet through Jell-O, making the Jell-O shake a little, this nugget coming through the Earth made the Earth shake a little. And you would like to therefore claim that strange quark matter has in fact been discovered. Trouble is, nobody believes this either. And the problem is, it's only one. I mean, nobody's going to believe just one, right? You're going to have to get more. But the problem is, they searched the whole 1993 data set, and it was the only set of data that really works out. So they're, I don't know if they'll find another one or not. But it's a possibility. And the fact that there's this one possible event that is, the paper has been accepted for publication and will be published. So it's not, just somebody made this up. They do have evidence of this. It's a possible sign that this sort of thing has really happened. And in fact, when they first reported this, we did have a headline to this effect. So it's another headline, not quite from the future yet, but from the near past. Now, let's get to the real future. Susie is not the physicist's girlfriend. It's a shorthand terminology for what's called supersymmetry. Supersymmetry it's a mathematical thing, okay? I'm not going to go into it. But it's what a lot of people think will make it possible to explain some of the really deep mysteries of the universe, especially in terms of what most of the matter in the universe is. So if you were to take a census of all the matter and energy in the universe, and you remember Einstein said matter and energy are like interchangeable, so it's all the same kind of thing. And you took an inventory of all the contents of the universe in the form of matter and energy, you'd find that 70% of it was something called dark energy. That's physics technical terminology for we don't know what the hell it is. Something like 25, 26, 27% is dark matter. And in fact, the more technical term describing it a little more thoroughly is cold dark matter. And of course, again, they don't know what it is. That's why I call it cold dark matter. But I said that to my wife, and she said, I know what it is. It's the stuff in the back of the refrigerator. Only a little bit, 3-4% maybe, is ordinary matter. The stuff that you and I are made of, the stuff that planets and stars are made of, makes up a tiny bit of the whole mass energy recipe for the universe. So this is very mysterious. I mean, this is a serious problem for scientists who are trying to say that they know what's going on out there in the universe. They know a lot, but they don't know some pretty big things. So, for example, dark energy. There has been progress on understanding the dark energy because we now have an image of what it looks like. This was difficult to obtain. I actually stole this slide from a famous cosmologist named Rocky Cobb who worked very hard at acquiring this data. So I'm sorry, I just took his instead of doing the research myself. This is progress. Similar progress has been made on dark matter. So you now have a pretty good idea of the depth of understanding of the problem. But it's not hopeless. It's not hopeless. We know pretty much about the matter of the universe. We know the basic particles and basic forces in the universe. It's called the standard model of particles, of particle physics, or the standard model of particles and forces. This is an enormous achievement to figure all this out, by the way. We know that there's these 6 quarks. We know that there are 6 companion particles called leptons. That includes the electron. That's what makes up ordinary matter. All ordinary matter is made up of these things. We know that there are 4 forces. There are electromagnetic forces, there are weak and strong nuclear forces, and we know the kinds of particles that transmit those forces. This is a great achievement to be able to figure all this out. But of course it doesn't explain everything, so like the dark matter, for example. So it's conceivable, and there's mathematical work, just like what I've been telling you earlier, where people have been fiddling with squiggles on paper and say, hey, there could be, for every particle we know about, there could be another particle, a partner particle, a super partner particle. The super coming from this idea of supersymmetry, which is basically saying the symmetry is we got all these particles on the one side. To make it symmetry, we got to have every one of those has to have another partner on this other side of whatever slide you're showing. And they have funny names. The regular photon, its super partner would be called the photino, gluon would be called the gluino, Z particle would be called the xeno, W particle would be called the wino. And the quark, for every quark, there would be a squark. For the electron, there would be a selectron. So again, these clever names really help in making progress in physics. So do these supersymmetric particles really exist? Well, there is an experiment. There are several experiments, actually. Here's an example of one experiment that's being done to try to find them. If they exist, they should be flying through all of space. And if so, the Earth should be running into them all the time. So what you do is you build a little detector, put it down deep below ground where other stuff won't bother it. You say, OK, Earth, head on out through space, and it will. But you have to keep in mind that when it's summertime, the Earth is not only moving itself around, it's not only moving itself through space, the sun and Earth are all moving together through space. And in summertime, the Earth is moving along with the sun, but in wintertime, the Earth is coming back around the sun this way, so the Earth is going the opposite direction. So it's like when you're driving your car forward into a bunch of mosquitoes or backwards away from them, you're going to smash more mosquitoes when you're going forward, no matter what the mosquitoes are doing. So the idea was, in the summertime, the Earth going this way, as we show down here, it would be running into more of these particles than it would be in the wintertime when the Earth is going away. So if you did this experiment over a few years and found more hits in the summer than the winter, you would conclude, aha, we're running into these particles, these supersymmetric particles. We've detected the dark matter. And the people who run this experiment in Italy have been for 4 years saying, yep, we keep seeing it, we found the dark matter. Trouble is, nobody believes them. And I think there's probably good reasons. They have reasons for not believing them. It's just not like they don't like the Italians. The reason is other experiments have been done that if this experiment was right, the other experiments would have seen something too, and they don't. So they figure there's something funny in the instrumentation or something's going on. It's not entirely clear that they're wrong, but it's certainly not good enough evidence to say, yep, we found it. Now, these particles, these supersymmetric particles, have a particular set of properties that make them likely candidates to be this missing dark matter. They are weakly interacting, which in other words, they're hard to detect. You got to build these if they were easy to detect, you wouldn't have to go down in the mine with your sensitive little detector. You could, see them easy, find them some easy way. They're weakly interactive. They're very massive compared to the particles we know. That's why we haven't been able to make them in our particle accelerators yet. We make a lot of particles in particle accelerators, but these are so massive they take more energy to make than we've been able to muster so far. So they're weakly interacting massive particles, which invites another new physics term, technical term, of WIMP, to be used to describe them. Well, They're not the only candidate, though, for what these dark matter might be. Suppose there's another kind of particle that's even more massive than WIMPs, which leads us to our next potential headline. And this is another term that was invented by our friend Rocky Cobb, who, you know, you're not going to tell him I used all his stuff, are you? He says, the question is dark matter WIMP or WIMPzilla? Well, most physicists and astrophysicists today would still be on the WIMP side. They're really favoring the WIMPs. And the evidence probably suggests WIMPs are more likely, but we don't know yet. WIMPzillas would be way, way, way more massive than WIMPs, so there wouldn't need to be as many of them to make up the dark matter, and so they might be harder to detect. And the reason we don't detect them is just because they're hiding somewhere. They might be hiding in the middle of the sun or something. I don't know. But someday they will burst out and surprise us. And this idea came, again, from working, this time using computers to study what was going on in the early universe. And they put all the equations into the computer about how to calculate what's going on in the early universe. And the answer kept coming out. There was these massive dark matter particles. And Rocky says, what the hell is this? They didn't put that into the computer. The computer spit it out because the computer was analyzing the equations and the math and said these things ought to be being made. So the possibility exists that this is another case where the people doing the mathematical study have figured out something exists before the evidence is found. Now we get to my most favorite prediction of all, I think, which is, I think if this turns out to be right, it would be probably, I mean, it'd be one of the most fantastic discoveries in the history of all humankind to be able to say there are more universes than ours. Now, when I was a little kid, if you asked a question like, how many universes are there? And you say, stupid kid, there's only one universe. That's what it means. The universe is everything. That's all there is. You can't ask about other universes. You mean other galaxies or something like that. Well, like a lot of stupid little kid questions, it turned out to be not such a bad question. Because when the people who were saying that got busy trying to figure out how the universe we knew about got here, they got some surprises. Now, just to give a little perspective here, I want to do this quickly so we're all understanding the concept. The galaxy, this is our galaxy. This is Milky Way galaxy, okay? This is a collection of, 100 billion or so stars, of which our sun is one. We live on a planet around one of these stars. And so where are we? We're right here in this galaxy. Now, that's a lot of space. This is a big thing, this galaxy. But you go out 1,000 times farther. In other words, what was, this is now where this distance here is 10 million light years. Our galaxy is one of these little white dots here that was filling up the screen a minute ago. And you got all these galaxies all out in space at great distances, millions of light years away from us. If you go out by 10,000 from the original picture, you see there are clusters of these white dots all throughout the cosmos. And this, we're getting farther and farther out. There's a lot of galaxies, and we were this little speck in one of them. And if you go out way out and get a picture of what the whole visible universe might look like, you've got this whole network of clusters of galaxies spread out all over all this space. The universe is pretty damn big. Now, however, it was once very small. 14 billion years ago, the universe was no big deal. We are quite sure from all the things we know, the math and the observations, that the universe was extremely small, extremely hot, extremely dense, and then started getting bigger in a Big Bang, which is what we call the beginning of the universe, the Big Bang. When it first started up, maybe a trillionth of a trillionth of a trillionth of a second or so after things first got going, it was maybe roughly this size compared to, and this is even cheating, this is just the nucleus of an atom. That isn't even the whole atom with the electrons out here. So the universe is very small. And it expanded in that first tiny fraction of a second at a tremendous rate to get big enough to then expand at a more leisurely rate into the universe we see today. So here's the tricky thing, though. That really big burst of expansion right at the beginning burst only a little part of the universe up that we can see. The visible universe that we know about today started from just one little region of what the whole universe was. So guess what? When scientists work out how this can work and how our universe could come to be the way it is, look the way it is, be the size of the way it is, have what's in it's in it, they are forced to the conclusion that if it happened once, it could happen again. Another part of the very early universe could also have blown up into another entirely different universe, just like the one we are in and see. There could be not only another universe parallel to ours, but all kinds of universes like ours. Now, this is very hard to comprehend, I think. The fact that this vast amount of space that you can't imagine to begin with is just one little piece of all kinds of similar, equally big masses of space. But it's possible. This is the sort of thing that the equations that the physicists write down to explain what we see, and they explain a lot of what we see, those equations also include the possibility for this sort of thing to happen. So I think you have to take it seriously. And Andre Linde, one of the pioneers in this theory in this area, just says it flat out. I mean, the universe, there was not just one big bang for one universe. There were a whole lot of big bangs. And he really believes this, and a lot of other people, I think, are coming to believe it too, that it's hard to escape this possibility. Now, if any of you have been watching the PBS special on superstring theory that was last week and this week, yesterday, I guess, you already know everything I'm going to say about superstrings because they did a really good show about it. But this is another example of something that scientists have studied thoroughly in the hopes that it will answer the questions they have about the nature of matter in the universe. There's no evidence yet that this is a correct theory, but it looks so good that so many people are working on it, there's just almost this sense that there has to be something right about this. The basic idea is that the particles we've been talking about all this time are not really little tiny balls, but they're little tiny pieces of string that wiggle around. And in fact, the different particles we see just look different because the little string is vibrating in different ways. Just like, a musical instrument can play different notes with the same string, nature can have different particles by one string vibrating in different ways. So the quark with the two ups and the down, or the proton with the two up quarks and the down quark in it, if you could some way magically magnify it, you'd see what you really have in here are little strings. And in fact, this is one of the only ways people know how to explain why you have the force of gravity in the world. It doesn't fit in any other way unless you can have particles made of strings. Whether it ends up working, I don't really know whether it will or not, but it's a very important idea. Now, if you notice, here's a little clue. Sometimes these strings are just loops, sometimes they just have ends, but the ends have to attach to some little piece of cellophane here or something. Maybe you could think of it as a membrane. And the clever physicists, of course, always eager to save a syllable, refer to membranes as brains. And it very well could be that the parallel universes I was talking about a minute ago are not the only kind of parallel universe could be. Those parallel universes would be too far away to ever go there. They would be outside the reach of our eyes, our spaceships. No light, no signal, nothing. There's no hope. Now, there's a possibility, though, that space is more complicated than we know. This is from the book Flatland. It's a very famous book. You should all read it if you ever get the chance. It's about a world of two dimensions where there was a flat sheet of paper kind of world, and everything was two dimensions. But then someday one guy got a visitor from a circle that kept getting bigger and then smaller and smaller, then it would get bigger again. And he realized it was a sphere moving through his sheet of paper that he lived on. And that's what made the circle grow bigger and smaller as the circle moved through it. So the concept is now that maybe our universe is like that. Maybe the three dimensions that we live in are just part of a bigger dimensional space, and that our three-dimensional world, up, down, this way, that way, whatever, you know, if you're on the surface, latitude, longitude, altitude, you can specify any position with 3 numbers. Our three-dimensional world is sitting in bigger dimensions that we don't know about. Well, if so, imagine, think about it this way. Imagine our universe is like a page in a book. And the words on the page are like the galaxies of stars, or the ink is like matter, and the ink is stuck to the paper. The ink can't get off the paper. For those words that live on this page, they only know the 2 dimensions. Maybe they can see the word in the next line over, and the word the next line above and below, and the next word over. So they know there's 2 dimensions on this page, you know, this way and this way. They have no idea that there's this third little thin dimension of the page, and they have certainly no idea that there are other pages. If the ink's stuck on the paper, it can't go anywhere else. Our universe could be like that. Our universe could be stuck in a different dimension, another dimension of space, where all our space is just like a slice sitting within that other dimension. This is hard to get, isn't it? That's why it makes for such a good book, you know. Anyway, if we're like that, though, if our universe is like that, then there could be another universe sitting in that same other dimension, just, you know, like a page, like the next page in the book. There could be a whole lot of universes sitting in here, like a whole lot of pages in a book. So, you know, how can you fit a lot of universes in a little dimension that's maybe a millimeter high? Well, saying your book is only this thick, it can have 300 pages stuck in there. And you don't think about the fact that each page has that third dimension that is very thin and allows a lot of them to be stuck in there. So our universe could be just one of a whole stack of universes stuck right next to each other. Now, why is this an interesting idea? Well, remember the dark matter slide? There's all this dark matter out there that we don't know what it is. We think it's there because we see the way the galaxies spin and the way the galaxies fly around. They're being pulled by some matter, some gravitational force that we can't see. If it was just other stars, we could see it. So there's some matter that's exerting gravity. But suppose it's just ordinary matter, but it happens to be in a parallel universe. We can't see it because light can't jump from one universe to the other. But gravity can. Gravity can go wherever the hell it wants. So when we look out from our galaxy here and see, oh, there's weird stuff going on here, there's some dark matter, maybe it's just another galaxy in this parallel universe right next door. It's possible. Can't guarantee it. And Lisa Randall is one of the famous physicists who established this idea a few years ago that our universe could be one in a bigger space, that there could be these other dimensions of space that our universe could just be one little slice through. This last one I'm going to skip, just basically say there was a story in the paper a couple weeks ago about the universe being the shape of a soccer ball. It is very hard to explain. I'm not going to try to explain it. It was wrong, so I don't really feel compelled to explain it. But it could be. It was only wrong because they thought it was a small soccer ball. It's still possible it could be a big soccer ball. But anyway, I'm going to end then. That was the paper Nature. I'm going to end then just by saying that what does this all tell us about the nature of the universe? I mean, it tells us, apart from all the weird stuff that's out there, there's something very strange about how we can do math and figure out things about reality. There's something unusual, as famous physicists have remarked, about how our equations capture some of the reality of the universe. Before we even look out there, we can figure out things that are out there with our equations. And as Hertz said, commenting specifically on where I started with Maxwell and the radio waves, it was like the equations had their own intelligence, that the equations gave you back more than you put into them. And I think that's really an interesting mystery. And Poincaré, a great mathematician, said, you know, part of the reason just may be that reality is an elusive concept. And if we're saying we're finding out things about what's real, How do we know what's real? It gets into very deep issues. And I think the final word will come to the inventor of quantum theory, Max Planck, who, giving a warning to all speakers like me when I get to this part of the talk, is that great caution must be exercised in using the word real. Thanks. Are there any questions?
Are there any questions?
Somebody's thinking of some question. There's one.
When you were talking about the Big Bang Theory and how everything came from one point smaller than the nucleus of an atom, how could so much density be in one small point?
Excellent question. That's exactly one of the questions that the superstring theorists are trying to figure out. How could you get that much density into one small point? And I mean, the actual answer is you don't know exactly yet because you don't have the theory that goes all the way down to the point. You have the theory that works pretty well going down to 10 to the minus 32nd centimeters, but getting smaller than that, the equation